All right, guys, now that we've gone through all of the details about routing and transport locators, everything else regarding the unicast routing concepts within the SD-WAN fabric, we're going to spend some time talking about route redistribution, and we're going to go into a deep dive into network segmentation. So we're going to talk about how redistribution works in the SD-WAN fabric. We're going to talk about the origin and suborigin types that are used for routes. We're going to list the administrative distances and talk about what administrative distance represents for various routing protocols. We'll also take a look at the steps that are used in the best path algorithm to allow us to avoid loops in the topology as well. And then we'll talk about how VPN routes get separated with the use of that segmentation, and then finally how the routes are propagated in a segmented network. All right, so obviously what we want to do in this particular case is we want to talk a little bit about some of what we already talked about in the last section, just to make sure that we can review this discussion and understand where we're coming from with respect to routing in the SD-WAN fabric before we actually get into the specifics of redistribution. Now, what we refer to this as, just all of these concepts that we've been discussing in the previous sections as well as this section, is what we call unicast overlay routing. The overlay network, as we mentioned previously, is controlled by the OMP, right? The Overlay Management Protocol, and it allows us to create these policies, control the policy propagation, as well as all of the routing information and reachability information across the network. The OMP protocol is really the one that's responsible for establishing and maintaining that control plane. It provides that orchestration of the overlay network, especially the overlay network communication, including the connectivity between the different sites. It is used to manage the service chaining processes, the VPN technologies, the distribution of service level routing information, and also those location mappings, right? The distribution of data plane security parameters, central control and distribution of our routing policies, and so on. So OMP is really that control protocol that's used to exchange all of our routing information, our policy information, and the management information between the vSmart controllers and those vEdge routers inside of our SD-WAN fabric and inside of our overlay network. As we mentioned before, it's obviously enabled by default. Once you start those vSmart controllers and vEdge routers, we don't really have to explicitly enable the protocol. All right. The route advertisements themselves, we didn't really get into specifics in this regard, but I do want to take a chance to kind of go through that before we get into the actual redistribution. On our vSmart controllers and our vEdge router, OMP is going to advertise to its peers all of the routes and all the services that it's learned from the local site. That also includes corresponding TLOC mappings or transport location mappings. These OMP routes, as we mentioned previously, they are called vRoutes. We interact with traditional routing protocols, and we interact with the traditional overlay network environment, but the notation of the routing peers is going to be different from the traditional network environment. From a logical point of view, the overlay environment consists of a centralized controller, and then we have various numbers of edge devices, with each edge device advertising its own imported routes to that centralized controller. And then based on whatever policy decisions that we've defined, the controller then distributes that overlay routing information to other edge devices in the network, right? And again, we've talked about this in some of our previous lessons. It doesn't hurt to kind of go through it again, right? Now, one of the critical things to understand, though, is that the edge devices never advertise routing information to each other. Whether it's with some sort of IGP or some sort of standard exterior gateway protocol, or whether it is using OMP. The peering sessions are always between the centralized controller and the edge device, and that is exclusively what's used to exchange all this control plane traffic. All right. In addition, in that same regard, those particular tunnels are never going to be used for data traffic either. All right, so there are V routes that we advertise, right? Those are the prefixes that allow us to establish that reachability between the endpoints by using this OMP manipulated or OMP controlled transport network. The routes represent basically in a central network or in the SD-WAN fabric, things like services in a central data center, services that we might have at branch location, reachability information to reach different hosts or other endpoints in the network, and so on. The OMP routes themselves play a very significant role because they're required to resolve those TLOCs so that we can perform that functional forwarding. Now, if we compare this to, say, like BGP, an OMP route is kind of equivalent to the fact that we might be carrying a prefix like I said previously, in that BGP address family field. All right. The transport locators, the TLOCs that I call them TLOCs, those are the identifiers that tie an OMP route to a particular physical location. It's the only entity of the entire OMP routing domain that is visible to the underlying network. And it does have to be reachable through that routing in that underlying network. Now, those TLOCs can be directly reachable with an entry in the routing table of a physical network, or they could be represented by some sort of prefix on the outside of a NAT device, but that still has to be included in the routing table. All right? We'll think of this kind of like our next hop attribute, if we will, like we see with BGP. And then we finally have our service routes. So our V routes, our TLOC information, and our service routes, which basically identify services on the network for service chaining. That might include things like firewall feature sets, intrusion detection systems, load balancers, application aware intrusion, or inspection, if you will, and so on. All right. Now, the OMP routes can be comprised of different types of site local routes. They can be connected routes, which we refer to in the SD-WAN fabric as a direct route. They could be static routes, they could be BGP routes, or they could be OSPF inter-area, the type 1s and 2 routes, intra-area would be the type 3 routes, intra-area would be those type 1 routes, and then our external routes would be either OE or ON routes that are coming from an ASBR. All right. Now, the route advertisements themselves have a lot of different variables, and I'm not going to go through this again in detail because we went through this in the previous lesson. So if you want to go back and review that, feel free. But we have the TLOC information, we have the origin, we have the originator, we have the preference, we have the service, the site ID, the tag, and the associated VPN. Now, we can configure some of the OMP route attribute values, things like system IP, route color, encapsulation type, carrier, preference, site ID, and VPN. We can modify those attributes by provisioning a policy, what we call a control plane policy, on our vSmart controller to control reachability through the SD-WAN fabric. Remember, those TLOC routes basically identify our transport locations. Those are going to be comprised of those 3 tuple values that consist of a system IP address of the OMP speaker, the one that's actually generating the OMP messages, a color, and an encapsulation type. So the TLOC, again, talked about this in the previous lesson. I'll just review it really quickly. We have our private and public addresses. We have a carrier. We have a color, an encapsulation type, a preference, a site ID, a tag, and a weight. All right. Now, the IP address that's actually used in the TLOC is the fixed system address of the vEdge router itself. The reason for not using an IP address of an interface to represent that particular TLOC address is that if that interface goes down, maybe that interface is being allocated an address through DHCP, which is not uncommon, or an interface card gets swapped or whatever, we want to make sure that we have stability in the domain. So typically we would represent that system IP or system address as some sort of loopback interface or some sort of interface that's not going to change. All right, the encapsulation, like I said, can either be an IPsec or a GRE encapsulation 99% of the time. It's going to be an IPsec encapsulation. All right. Now, we also have service routes, right? Service routes represent the services that are connected to the vEdge router or to the local site network where that vEdge router resides. The vEdge router advertises those routes to the vSmart controllers using the service address family, network layer reachability information. We talked about this in a previous lesson when we talked about the concept of service chaining. And that was something that we spent a little bit of time talking about. Now this brings us to really our topic at hand, right? Which is OMP route redistribution. OMP actually automatically redistributes different types of routes that it learns either locally or from its routing peers. And those routes would include connected routes, static routes, OSPF intra-area routes, which are my O routes, right? The ones that are represented with it as a type 1 LSA, and my OSPF inter-area routes, which are represented as my type 3 LSAs, my summary LSAs. Now, to avoid routing loops and maybe even injecting some sort of asymmetric path or less optimal path in the process, we have to explicitly configure redistribution for BGP routes and those OSPF external routes. The idea is we're trying to avoid propagating excessive routing information from the edge to the access portion of the network. So the routes that the vEdge router receives through OMP are not automatically redistributed into the other routing protocols running on the other routers. In other words, going the other direction. So if we want to redistribute the routes received through OMP, we have to enable this redistribution process locally on each of our vEdge routers. One of the things that happens in this process of redistribution is that OMP sets what we call the origin type for a particular route. But before we get into that, I just want to make sure that we hit up all these different slides. We're going to see the origin type slide here in a minute. Like I said, OMP routes to the service side. That site local redistribution doesn't happen automatically, right? We have to make sure that we do that redistribution explicitly to get routes from the SD-WAN fabric into the local side routing protocols. So route redistribution is basically a multi-step process, right? Step one, it shows us here that OMP learns OSPF routes. Those routes then get sent up through the control plane session to the vSmart routers. So the vSmart router is going to learn those OSPF routes. vSmart is going to then apply whatever service policies that we have to those particular routes. You know, whether we're going to filter those routes from one vEdge device to another, whether we're going to allow those routes and so on. We apply those policies to those particular routes. And then in step 4, we reflect those routes. If you recall, I mentioned a couple of times that the vSmart controller acts pretty much like a route reflector in a lot of environments, where like a BGP route reflector, where it takes all that information that it learns from one vEdge router and reflects them to the other vEdge router. So those routes, if the policy permits and if the tunnels are established, will then get reflected to other vEdge devices. And then if we choose, if we want to, we can then configure explicitly to allow OMP to redistribute those routes back into the site local location or the site local routing protocol if we need to do that. Right? That again doesn't happen automatically, but it is something that we can configure if it's something that we want. All right? Now, as I started to kind of allude to, we have different origin and suborigin types that are identified with these routes within the SD-WAN fabric. right? OMP actually sets the origin and suborigin type for each OMP route, which indicates the route's origin. All right, now when we're selecting those routes, the vSmart controller and the vEdge routers take that origin type and subtype into consideration. So BGP, for example, would be the origin type for routes that are coming from BGP, and then the OMP route origin subtype could either be BGP internal routes or BGP external routes. Connected routes don't have a subtype. OSPF could come in as external type 1 or external type 2. Now that means that both external 1 and external 2 represent essentially how we deal with the metric. When those routes are injected, type 2 would be kind of the default where the metric, the seed metric stays the same, and type 1, the seed metric would be modified in that redistribution process. But we'll get into that in a little bit more detail later on. All right, and then we have our intra-area routes. Those are routes learned within an area, and our inter-area routes, those are the subtypes for those. And static routes don't have a specific subtype. OMP also carries the metric of the original route. The only time you would ever see a metric of 0 would be if it's actually a connected route in this scenario. Now, the next thing that we talk about is something that you're kind of probably familiar with if you've dealt with routing protocols on a regular basis, and that is administrative distance. Administrative distance provides us the ability to specify the trustworthiness of the address information source, assuming that the information we're receiving is identical. So, for example, if I learn about a 10.10.10/24 prefix from EIGRP, and I learn about a 10.10.10/24 prefix from BGP, I would inherently, well, depending on what type of BGP, I would inherently trust EIGRP over BGP. But keep in mind, we're talking about the exact same information, right? We're not talking about a 10.10.10/24 and a 10.10.10/25. Those prefixes are unique, and if both of those were learned through different sources, both of those prefixes potentially could go into the routing information base. So administrative distance is really the measure that we use to select the best path when we have two or more different routes to the exact same prefix destination with prefix length from multiple information sources. So when the vSmart controller or the vEdge router is selecting an OMP route to a destination, it's always going to prefer the one with the lower or the lowest administrative distance value. So as we can see from the table here, a connected route has a standard administrative distance of 0. Static routes have an administrative distance of 1. NAT translated routes, which would eventually overwrite static routes anyway, also have an administrative distance of 1. Routes that we learn from DHCP in the DHCP address allocation process will have an administrative distance of 1. Routes that are learned over GRE will have an administrative distance of 5. Exterior BGP or external BGP routes, standard administrative distance of 20. That's kind of the standard in the industry. OSPF 110, again, the same throughout the industry. But keep in mind with OSPF, we can control with our policies, our feature templates, we can control that administrative distance value based on external or intra or inter-area routes. So we can actually adjust that value for each of the three types of routes. Internal BGP, also pretty much a standard 200, and then OMP has an administrative distance of 250. So you think about this, you say, okay, well, wait a minute. OMP is what I'm using to exchange information. Why is it the least trusted protocol? Well, if I'm on a vEdge router and I'm learning about a 10.10.10/24 prefix from OSPF, and I'm learning, meaning a client-side route, right, on the LAN side, and then I'm also learning about the same prefix through OMP, naturally I'd probably want to trust the one that I'm learning locally as opposed to the one that's being sent over the SD-WAN fabric. So that's why we typically trust those OMP routes the least. So how does OMP use, or what best path algorithm does OMP use? And by the way, what kind of loop avoidance mechanisms do we have built into this particular topology as well? These are very important concepts to understand, right? Because when it comes to routing, when it comes to prefix routing and trying to identify destinations, it's really important to identify kind of those standard elements of protecting our routing domain, right? We want to make sure that we don't have asymmetric paths. We want to make sure that we're choosing the optimal path for our destination. We don't want to choose suboptimal paths for routing. We also want to make sure that we have loop avoidance mechanisms in place. So the vEdge routers advertise their local routes to the vSmart controllers using OMP, right? Now, depending on the network topology, some routes might be advertised from multiple vEdge routers. So we use a particular algorithm to choose the best route. The first thing we check is whether the OMP route is valid, right? Just because it's being learned doesn't mean it's valid. And what would cause an OMP route to not be valid? The TLOC information is not reachable, right? We've identified the next hop through that TLOC information, but we can't reach that TLOC address. That's one reason why maybe a route might be learned, but the destination is not going to be reachable. We go to step number 2. If the OMP route is valid, and if it has been learned from the same Viptela device, we select the OMP route with the lower administrative distance, right? So again, we're talking about learning about essentially the same prefix from 2 different routing information sources. Administrative distance pretty much trumps everything in that regard. We don't look at metrics, we don't look at anything else. Of course, prefix length wouldn't come into play here because we're talking about the exact same prefix. So naturally, administrative distance would be the next logical choice, right? And that's the way it works in standard routing domains. Administrative distance takes precedence over metric choice or over longest match routing. Obviously, longest match routing, again, wouldn't come into play here because we're talking about the exact same route. So let's assume we've gone through now, we've selected the best route based on lowest administrative distance. If those administrative distance are equal, if the administrative distance values are equal, we select the OMP route with the higher OMP route preference value. Now, we had talked about that previously in one of our previous exercises. The default preference is 0, and we can set the preference through policy to identify based on information that we're learning from this peer or that peer, what that preference is going to be. Preference is going to take precedence over weight. Weight is another value that can be established, and so preference is what's going to be used. Now, if we're on the vEdge routers, and this would actually happen only on the vEdge routers, if those OMP route preference values are equal, we select the OMP route with the higher TLOC preference value. Again, that is a value that we can configure, and we're looking to create an additional tiebreaker. Okay? If the TLOC preference values are equal, then we start to compare things like the origin type. And we actually select the route based on its origin, and it's going to be a first match rule, right? So we're going to take connected routes over static routes. Then we're going to take our eBGP routes. Then we're going to take our OSPF intra-area routes. Then we'll accept our OSPF inter-area routes. Then our OSPF external routes. Finally, our iBGP routes. Hopefully we haven't gotten down to this point. And then finally, unknown, meaning unknown origin type. All right. Now, if the origin type is the same, OMP will choose the route that has the lower origin metric. All right, again, those metrics are going to be carried over from the protocols. On our vEdge routers, if the origin types are the same, we select the route from the vEdge router that has the higher router ID. So at this point, we really shouldn't be in a situation where we have a tie, right? Because the router ID values should be unique based on standard design and implementation practices. But there is one more step. All right. If the router IDs are equal, the vEdge router then selects the OMP route with the higher private IP address. If the vSmart controller receives that same prefix from 2 different sites, and if all the other attributes are equal, we're going to choose the path. Well, basically in this particular case, we would actually just go ahead and choose both of the paths, and we would do some ECMP. Okay? So just to review, and I forgot to change the slide, so I apologize for that, but this is exactly what I was just referencing in our discussion here. Connected, static, eBGP, OSPF intra-area, OSPF inter-area, OSPF external, iBGP unknown, and then we select the route with a higher router ID, and then we select the route with a higher private IP. So what I'd like to do actually on this particular slide here, since I didn't pass through it before I went through the next through the discussion, is I want to walk through a couple of different scenarios, right? Let's say, for example, the vSmart controller receives an OMP route to 10.10.10.0/24 from a vEdge router, and that has an origin code of OSPF, all right? But we also received that same route from another vSmart controller, also with the origin code of OSPF. Now, assuming that all other things are equal, we're basically going to choose the route that came from the vEdge router, not from the other vSmart device. All right. Now, let's say vSmart controller again learns about that same OMP route, 10.10.10.0/24, from two different vEdge routers at the same site. If all the other parameters are the same, both routes actually get chosen and actually get advertised to those other OMP peers, because remember, we have the ability to load balance up to 4 equal cost routes, which can then be selected and advertised. A vEdge router installs the OMP route in its forwarding information base, but only if that transport location address that it points to is active. What has to happen for that to occur? Well, for one of those transport location addresses to be active, we have to have, number one, an active BFD session. That BFD session has to be associated with that transport location address. And we know from our previous discussion, those BFD sessions are established by each of the vEdge routers, which creates this separate BFD session for each of our transport location tunnels. Right? Now, if one of those BFD sessions becomes inactive, the vSmart controller removes it from the forwarding table and all the routes as well that are going to end up pointing to that particular TLOC. So the vSmart controller runs this best path algorithm on all of the received paths that it receives, and it stores those best paths in that selection order, whatever that winning order is. It's going to store those paths. What it then does is it walks through this list and applies the outbound policy to each one of those paths. If a path isn't rejected by the outbound policy, that's when it's going to go ahead and advertise that information to its peers. There's a max number of configured send path limit paths for each prefix that get advertised. We talked about that previously, and that's also something that you can customize through the use of your feature templates. All right, so we'll just take a look at a couple more examples real quick, and then we'll get into a couple of other topics that I want to talk about before I move into the segmentation piece of this particular lesson. So let's say a vSmart controller receives 8 different paths for the prefix of 10.10.10.0/24. Okay? The send path limit is already set to 4. That's the default value that we have in our system. So when the outbound policy gets applied, the outbound policy doesn't actually reject any of those paths. It's just that the first 4 paths from the received best paths that are stored in the order are the ones that get selected. So we're not really necessarily filtering out specific paths. We're just almost, it's not quite, but almost like a first come, first serve type of basis. All right. Now let's say a vSmart controller receives 8 paths for 10.10.10.0/24, and that send path limit again is set to 4. All right. When an outbound policy rejects some of those paths, then the first 4 non-rejected paths are what are going to get stored and used. All right, which makes logical sense if you think about it. All right. Now, one of the features when we talked about our feature templates for OMP, one of the features that we talked about was graceful restart. We didn't really get into the details of what graceful restart was. We saw an option to change some of the values. What graceful restart does for OMP is it actually allows the data plane in the overlay network to continue functioning if for some reason the control plane stops functioning or becomes unavailable. All right? So what happens with graceful restart? If the vSmart controller in the network goes down, or if you actually have multiple failures and multiple vSmart controllers go down simultaneously, those vEdge routers can continue to forward their data traffic. They will actually do this using whatever their last known good information that they received from the vSmart controllers was. Now, when that vSmart controller comes back again or becomes available again, we establish that DTLS connection to the vEdge routers. The vEdge router gets updated, and then all of that current network information from the vSmart controller gets applied. All right. So the last thing we talked about, or one of the previous things that we talked about as well, is how the overlay network does support BGP and OSPF unicast routing protocols. These protocols can actually be configured on the vEdge routers in any VPN except for the two predefined VPNs, VPN 0, which is a transport VPN, and VPN 512, which is the management VPN. All right. We also know, based on our very brief redistribution discussion, that vEdge routers can redistribute route information learned from BGP and OSPF into the OMP protocol. Some of it's done automatically, some of it has to be done explicitly, and then we can use OMP to choose the best path in the network. When the local site connects to a layer 3 VPN like an MPLS cloud, the vEdge router in this particular case is actually going to act as an MPLS CE device, or a customer edge device, and it's going to establish BGP peering sessions to connect to the provider edge routers in that layer 3 MPLS VPN cloud. If the vEdge router or the different vEdge routers at different local sites don't connect directly to the WAN cloud, but are maybe one or more hops away from the WAN, and they're connected, say, indirectly through a non-Viptela router, standard routing has to be enabled on the vEdge router's DTLS connections so that they can reach the WAN cloud. This could either be OSPF or BGP. Typically it would be OSPF, but I have seen scenarios where the customer decides to implement BGP. In both of these types of topologies, BGP or OSPF can run over that DTLS connection that was created on the loopback interfaces in VPN 0. Again, that's our transport VPN, and that VPN is responsible for carrying control traffic in our overlay network. The vBond orchestrator, we haven't talked about that guy in a while, but the vBond orchestrator learns about this DTLS connection from that loopback interface. It's going to take that information, it's going to send that information to the vSmart controller so that it can track the TLOC related information. In VPN 0, we can actually configure the physical interface that connects to the vEdge router to its neighbor, either the PE router if it's an MPLS connection, or the next hop router for the local site, but we don't establish a DTLS tunnel on that physical interface. All right. So we're going to take a look at the concept of segmentation in a little bit. We'll go ahead and wrap up this discussion about redistribution, and we'll start to get into our segmentation discussion to wrap up this lesson. All right. We got a few slides on this, so we'll go ahead and go through this. We did talk previously about what the purpose of segmentation was at a very high level, what the need for segmentation is in our SD-WAN fabric. Now, creating the basic VPNs that are required by SD-WAN devices, it's actually pretty simple, and it consists of a couple of different steps. On the vEdge router, we need to create a VPN instance for the transport VPN. That's VPN 0 in the case of the SD-WAN fabric. We need to create a VPN instance for the management VPN, which is VPN 512, and that's going to be reserved for the management traffic. And then we need to create a third VPN instance for carrying the actual data traffic, which would be our service VPNs, right? And we talked about in detail in some of the previous lessons, specifically what the transport VPN is used for, what VPN 512 is used for. So I don't want to get into too much detail on that right now, but this is the first kind of part or process of configuring that segmentation. On the vSmart controller, we do the same thing. We create VPN 0 for the transport. We create VPN 512 for management. But the third step is slightly different, right? The third step, it's about creating policies that are going to allow us to influence routing and access control within those additional VPNs that we have in our network. And that's really what is kind of the important concept in this particular case. Now, for enterprise-wide VPNs, our Cisco SD-WAN devices support things like MPLS extensions to data packets that are then transported within those various IPsec connections. What you're seeing in this particular diagram is the location of the MPLS information in that data plane packet header. These extensions provide security for that network segmentation. Much like we have network segmentation with an MPLS VPN, we're seeing a similar concept with the SD-WAN fabric. All right, we need this security to support what we call multi-tenancy in the branch, or to even just provide basic segmentation in our campus altogether. All right, now Cisco implements this SD-WAN fabric using IPsec UDP-based overlay networks and using that IPsec UDP-based overlay network protocol with the encapsulation based on RFC 4023. The security that's provided by including things like an initialization vector at the beginning of each of the payloads in the ESP header allows us to add additional levels of security. We don't really get into the details of that in this class because it's kind of beyond the scope of the SD-WAN class regarding what is an initialization vector and so on. But it is calculated by the AES 256 process, specifically the CBC process, which is the cipher block chaining process. All right. So without getting into too many specifics, we're basically just talking about some of the general concepts of segmentation. There are some situations where it might actually be desirable to leak routes from one VPN into another. All right, could be an extranet where we're making, say, a portion of our internet, or intranet, excuse me, available to users outside of our organization. Maybe this is for a B2B partnership, or it could be maybe for the purposes of doing some sort of network transition. Maybe it's some sort of merger or acquisition. To leak routes across VPNs, we can actually create a policy called a leaking control policy on the vSmart controller, and that allows us to control route leaking from that central point of management. Now, one of the things that I want to mention before we move on is there are some restrictions here, right? We can't leak routes between the service side and the transport side, which is VPN 0. Export to, which is the function that we actually use to leak those routes, is intended only for service VPN route leaking. All right. Now, the purpose of this discussion is not really to get into the specifics with regard to the configuration itself, but it is a fairly basic concept, right? We will probably see this in our policy section, which is the last module that we're going to go through in this class, but we would basically create a site list of our sites, and maybe it's a business partner site or whatever, and we can identify those different site IDs. And we can actually create a VPN list as well for all of our business partner VPNs. And then we might actually create a VPN list for our enterprise to business partner connections. Maybe that's that VPN that we identify to allow that enterprise to business partner connection. So maybe we have a site ID of 10 or 20. We have a business partner VPNs of 100 and 101. and then we have an enterprise to business partner VPN of 200. Then we have to establish a control policy, and we can give it a name, whatever we want to call it, and we reference the routes, typically the routes from our business partners, which are 100 and 200. All right. The final thing that we do is we then go ahead and apply an action, and our action in this case is to export to, and then we can identify the VPN list, which identifies our enterprise network VPN, which is 200 in this case, and that allows us to send those routes. All right. One of the advantages of importing routes this way is access control, because we actually keep the business partner routes in a separate VPN, and we create some sort of extranet policy that makes sure that those business partner routes can't talk to each other and so on. So that would definitely be a reason to do that. So let's take a look at another example here, and this one we're going to have a visual for it. Segmentation occurs at the edge of the network or on those vEdge routers, and the segmentation information gets carried in the packets in the form of an identifier. So let's say that vEdge 1 in this particular topology subscribes to two VPNs, the red VPN and the blue VPN. The red VPN in this case is the prefix of 10.1.1.0/24, and the blue VPN is the prefix of 10.2.2.0/24. vEdge 2 only subscribes to the red VPN. That VPN is the 192.168.1.0/24 VPN. vEdge 3 subscribes to the blue VPN, and in this particular case, that is the 192.168.2.0 VPN. All right? Because each vEdge router has an OMP connection over the DTLS tunnel to the vSmart controller, it propagates its routing information to that vSmart controller. On the vSmart controller, the network administrator can then enforce policies to drop routes, to accept routes, etc., or to change things like TLOCs. Maybe we're doing some sort of traffic engineering, maybe we're doing some service chaining, or to simply change the VPN ID. You as the network administrator can apply those policies as an inbound policy or as an outbound policy on the vSmart controller. All the prefixes belong to a single VPN, and they're kept in a separate routing table. This gives us that layer 3 isolation that's required for different segments in the network. vEdge 1, for example, has two VPN route tables. vEdge 2 and vEdge 3 each only have one route table. The vSmart controller maintains the VPN context for each of the different prefixes in this particular case. Now, to propagate the routing information across the network, we use that VPN ID to be able to identify the VPNs. The VPN ID itself is actually carried inside the packet that identifies each VPN on the link. When we configure a VPN on the vEdge router, the VPN has a label that gets associated to it. And then the vEdge router sends that label along with the VPN ID to the vSmart controller. It's up to the vSmart controller then to propagate that vEdge to VPN ID mapping information to all the other vEdge routers in the SD-WAN fabric. The remote vEdge routers take that information from the vSmart controller. They use that label to send traffic to whatever VPN it's supposed to go to. The local vEdge routers, once they receive that data with that VPN ID label, they use that label then to remove or demultiplex that data traffic so that they can send it into the service side of the network or the LAN side of the network. All right, we've talked about this quite a few times actually with regard to what are the default VPNs that are provided for network segmentation. VPN 0, like I said previously, this is my transport VPN. It's used to carry control traffic over the secure DTLS or TLS connections between the vSmart controller and the vEdge routers, and between the two vSmart controllers and the vBond orchestrator. VPN 0 actually contains all of the device's information for the management interface, and all the interfaces are disabled by default. All right. So for the control plane to establish itself so the overlay network can function, you have to configure the WAN transport interfaces in VPN 0. Conversely, VPN 512, this is our management VPN. It carries all of the out-of-band network management traffic between all of the different devices in the overlay network. This one is actually configured and enabled by default. We can modify the configurations, again, by modifying the templates, but we can modify the configurations of this VPN. All right. Now, to segment the networks and user traffic locally, we would use any of those other VPNs, which are the VPNs that are not VPN 0 and VPN 512. We also, of course, talked about what the meaning of a transport locator is, and the idea of what that service is used for in the network. Okay? So we've kind of refreshed a little bit. We've added some additional information to some of the concepts that we had talked about previously. We talked about what routes get automatically redistributed in the OMP protocol, those static routes, the connected routes, the OSPF internal routes, intra-area and inter-area routes. And we talked about the need for loop avoidance. And so explicitly, we would have to redistribute BGP and external routes. We also talked about the origin code and the sub-origin type for each route that gets advertised. The vSmart controller and the vEdge router consider that origin type and subtype when they're selecting routes. That's part of the best path selection process. Administrative distance is going to be used, and we went through the concepts of administrative distance, which is not really any different than traditional administrative distance concepts. We did talk about the best path algorithm and how we decide to choose a particular route, all the different tiebreakers and so on, the 8 steps that we go through. We talked about each of those 8 steps. We then talked about network segmentation, not in a whole lot of detail because it can be a rather complex concept, a configuration from a configuration perspective and a policy-driven perspective. But when we do get into our policy section, we'll talk more about that. We also talked about how we propagate routing information across the network, what is the VPN ID, what is the label that carries the packet, and how the vEdge routers use that label along with the VPN ID, to the vSmart controllers so that we can control redistribution and propagation of those routes to the other vEdge routers in our overlay network. All right, so we'll wrap this lesson up. We have one more lesson left in this module. We'll see you guys there.